and welcome to History of the Atom. Atomic theory starts way back in ancient Greece with a philosopher named Democritus, who basically, like all philosophers, sat around doing nothing except thinking about the world around him. So while he was thinking, he realized he could break things in half and they'd be the same, and break it in half again and it's still the same, and keep doing that, so on and so forth. But he said eventually there's got to be a smallest piece, and that smallest piece he called the atom. Then everybody forgot all about Democritus because he argued with Socrates, and everybody liked Socrates better. So Democritus' work was lost to history for a really long time. Then we fast forward all the way to 1803. What happened in 1803? A British school teacher named Dalton came along. And he was doing experiments, mostly with hydrogen and oxygen, and he realized a couple of things about atoms. The first thing he said is that atoms are small particles. He believed that those small particles were small, they were indestructible, and they were basically small marbles. So he said everything is made of atoms. If the elements are different, the atoms look different than each other. If the atoms are for the same element, they look identical to each other. He also said that they can't be created or destroyed in a reaction. We have a name for that now. It's called the conservation of mass. We also know from Dalton that if you have a compound, it always has the same ratio of the same atoms. For example, H2O, which is water, is always H2O. But there's another compound using hydrogen and oxygen that has a different ratio of the atoms. That's H2O2, otherwise known as hydrogen peroxide. That's right, the stuff in your medicine cabinet. So be careful, those small numbers mean something. Around the same time that Dalton was coming to his ideas, a little bit after, Mendeleev came along. Mendeleev was a Russian school teacher, and he had a problem. He needed a way for his students to be able to memorize all of the elements and their properties. So he kept putting the stuff on index cards, rearranging things, until he figured out a way of organizing the atoms so that if they have the same properties, they were in a column with each other. He arranged them by their mass, something that he knew. So when he put things in order of increasing mass and in columns according to their properties, he came up with the periodic table. The reason his periodic table was accepted and lots of other ones that people came up with were rejected is because Mendeleev was able to predict elements that didn't exist. He could tell you the properties and approximate mass. And as it happened, two of those elements were discovered a few years after he published his periodic table, so everyone recognized that he was onto something. We're going to talk a lot more about the periodic table in Unit 3. But still, during all this time, Dalton, Democritus, and even Mendeleev, they thought that atoms were one tiny solid thing. So they were hard, they were round, they looked like marbles. Of course, we know now that atoms have protons, neutrons, and electrons, things that have charge. How did we make that discovery? Well, that brings us to 1897 and J.J. Thomson. J.J. Thomson knew that we had atoms. And he was playing around with something called a cathode ray tube. Basically, it's a small tube full of gas. And he realized that when he hooked up to electricity, it would glow. So he said, well, I don't have anything in there to make it glow. So atoms must have something in them that conducts electricity and glows. So he called that an electron. But he realized that these electrons are really, really tiny. So it couldn't be the whole atom. He also knew that atoms were neutral. They didn't have an overall charge. So he knew there had to be this positive, massive thing that was an atom, and that these electrons were these tiny light things sort of peppering it. So when he drew his picture, he thought it looked like a plum pudding. So you have your pudding, and the electrons were like plums floating in it. So this is called the plum pudding model. In 1909, Robert Millikan came along, and he designed this really clever experiment that lots of people talk about in both chemistry and physics. It's called the oil drop experiment. And what he was able to do was figure out the mass of an electron and the charge of an electron. Back when Thomson discovered the electron, he knew the mass to charge ratio, but Millikan was actually able to separate that out. How did he do it? He took oil drops and he sprayed them through a positively charged plate, and he looked through a telescope to see what was going on. And he found that the oil drops stayed in between the two plates. And he was able to measure the size of the oil drops and see where they stayed in between the plates. And from that, he could figure out the charge and the mass of his electrons. A couple of years later, in 1911, Ernest Rutherford came along. I want to make sure everybody can see his name. Ernest Rutherford is an SOL favorite. They always ask him. So if you remember nothing else from this lesson, remember Rutherford's experiment. Rutherford passed alpha particles through gold foil. So he had a really thin sheet of gold foil. And he gave off alpha particles, which you'll remember from the last lesson, is a helium nucleus. And it has a positive 2 charge. So what he did was he detected where the alpha particles ended up after getting shot through the gold foil. And what he found out is that most of them went straight through. Well, this is a big surprise because he's putting it through a solid. But most of the alpha particles actually went straight through. So from that, he concluded that atoms were mostly made of empty space. But, not everything went through. Some of them did get blocked. So there has to be something in the middle of that empty space. And what's more, since it didn't bounce right back out, it couldn't be those electrons that have a negative charge. Oops. So what he actually discovered is the nucleus of the atom. And he is often credited with discovering the positively charged protons. But the important thing is he discovered that atoms are a small, dense, positive nucleus, and it's surrounded by mostly empty space. Eventually, Chadwick came along in 1931, and he discovered the neutron. That's the other thing that's in the nucleus. Neutrons have no charge, so they were much harder to discover. In 1913, 2 years after Rutherford said we have this small, dense nucleus with these electrons floating around, Bohr actually looked at the atom, and he was looking at emission spectra. And what Bohr realized is that the electrons are occurring not just randomly around the atom, but that they occur in distinct energy levels. We're going to use this idea of energy levels when we talk about how the periodic table is put together in Unit 3. But it's really important for you guys to know that Bohr discovered that the electrons are in energy levels, and his model is called the planetary model, or sometimes the boring model. Boring as in boring. And this is the model that most of you remember from biology at middle school, with a nucleus in the middle and rings around the outside with the electrons. Okay, and why does it get the name planetary model? Because it looks like planets orbiting the sun. one of the things that Bohr talks about is that they can jump from one energy level to another. But that's a discussion for Unit 3 when we talk about electron configuration. So now we went from ancient history, where atoms were these small hard spheres, to knowing that while atoms are the smallest particle of an element, they actually have pieces: protons, neutrons, and electrons. And we know roughly where they are. Protons and neutrons spend their time in the nucleus. Electrons are on the outside, for right now, in energy levels. But an amazing thing happened. When we learned about atomic number, Moseley, another Englishman, did a couple of experiments as well. And he figured out that the properties of the elements that Mendeleev put together just because they fit right, they actually go in order by atomic number of protons. Something Mendeleev couldn't have talked about because we didn't know about protons back then. So Moseley switched the order of the periodic table. Instead of increasing by atomic mass, he went up by atomic number. And that gives us the modern periodic table. A couple of things that are still to come when we talk more about the periodic table in Unit 3 is quantum theory. Where do we think the electrons are now? We already talked about Bohr said they're in rings. Well, we've got two other scientists, Heisenberg and Schrödinger, who helped to give our current quantum energy understanding of where the electrons can be found. Okay. But for right now, the key parts of the element: electrons, which are outside the nucleus. They have a charge of -1. That's the thing that gets gained and lost. That's the only thing that can change in an atom. They have a mass, but it's so small compared to protons and neutrons that we usually just ignore it. Protons are in the nucleus. They have the +1 charge. Okay, and protons are what identify the element. And neutrons are needed to hold the nucleus together, so we have enough mass to create the strong nuclear force that holds the nucleus of the atom together. Neutrons are also found in the nucleus. They have no charge. A change in neutrons gives us isotopes. So a couple of quick questions. Who was the first person to propose the idea that matter was not infinitely divisible? Take a second, come up with an answer, pause, and unpause when you're ready. Of course, the answer to that one was Democritus in ancient Greece. Which particle is not found in the nucleus of the atom? Again, pause until you have an answer. Okay, the correct answer to this one is the electron. Are gamma rays found in the nucleus? No, but gamma rays aren't a particle either. Dalton's theory also conveniently explained what thing? Remember back to about the second slide, we talked about atoms not being able to be created or destroyed, and that is an explanation of the law of conservation of mass. Thank you for playing Atomic History, and we'll see you next time.